So actually for the LC oscillator, we can have the solution to the second order ODE like this. So Q equals capital Q will be the maximum charge, or the charge, or the initial charge, times the cosine omega t plus phi, and here omega is 1 over LC as we derive. Okay, so this is the response, the natural response of the resistanceless or lossless LC circuits. Okay, so here we can have I equals dq dt, and then we can just plug in Q here and then take the derivative. So we have, when we take the derivative, cosine become negative sine omega t plus phi, and then for the chain rule, take the derivative becomes omega. So we have omega Q. So this is the expression of the I. Okay, so next we can consider the energy, the instantaneous energy stored in the E field and stored in the B field. So yeah, so actually UE is V squared over 2C, So actually we just plug in this expression here. So Q square will be capital Q square cosine square. So we have a capital Q square cosine square of this term, and then over 2C. So this is UE, and for the magnetic energy, or the energy stored in the B field, we have half of L, half of Li squared, or actually it will be nothing but Q square over 2C sine square omega t plus phi. Actually you can just find it here. Half of Li square will be half of L, and then here we have a square, so the negative square will be positive. So we have omega square Q square sine square of this term, and then don't forget omega is 1 over square root of LC, so it becomes L, and then this one becomes 1 over LC, because omega is 1 over square root of LC, so omega square is 1 over LC. So we have a Q square sine square. Okay, so here we can just cancel L and L. So we have Q square over C, and then we have also a 2 in the denominator. So it is Q square over 2C, which is actually this one, Q square over 2C sine square. Okay, so here we have some interesting thing, because this is actually cosine square of this term and then sine square of this term. So in high school trigonometry, you know that sine square of x plus cosine square of x is nothing but 1. Okay, so when we try to add them together, UE plus UB will be nothing but UE plus UB will be nothing but Q square over 2C, so which is a constant, because Q means the maximum charge, and then C is a constant, 2 is of course a constant. So this is a constant, which means that yeah, the total energy doesn't change as what we expect. Okay, so for the blue line it is UE, and then for the green line it is UB. And then they add up to be 1, because 1 is cosine, 1 is sine. So figure shows plot of a UE and UB for the case of phi equals 0. Okay, so for the yeah. Okay, so well, I think this figure is not correct. I think this this figure is not correct. I think this figure is not correct. So this is what this is cosine, this is sine, but this figure is something like they are just has an opposite sign. I think it should be like it should be like it should be like this. 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 They should have a 90-degree phase shift rather than 180-degree phase shift. So I think this one is not so correct. It's not so correct. And I think this should be t rather than half of t. Yeah. Okay, so but actually the maximum value of UE and UB are both q squared over 2c, and at any instant the sum of UE and UB to be a constant q squared over 2c. When UE is maximum, UB is 0. UB is 0, and conversely. Actually, this is correct. This one should be correct because it's already square. It's already square. So actually, this is correct. Yeah, this is q squared over 2c, and this is 0. So they adds up to be q squared over 2c. Yeah. Okay. This is correct. Okay. So let's take a look at this sample problem. So it says a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is then disconnected, and a 12 millihenry coil is connected in series with the capacitor so that LC oscillation occurs. What is the potential difference VL across the inductor as a function of time? Okay. Yeah. So first of all, we have the second order ODE, d2q dt2 plus 1 over LC q equals 0. Okay. Then we can get q equals capital Q cosine omega t. Here we don't really care about the phase, so let's just assume it to be 0 for simplicity. Okay, so here, yeah. So first, we can try to calculate capital Q. Capital Q here is like the battery is 57 volt. So, and then we also know the capacitor, so we can get Q to be C times V. So C is 1.5 times 10 to minus 6, and then V is 57. So this is 8.55 times 10 to minus 5 C. Okay, so VL is the voltage or the potential across the inductor, so which is nothing but L di dt. And I is actually the derivative of the charge, so it is nothing but L d2q dt2, which means that we actually need to take the second derivative of this equation. So d2q dt2 is nothing but negative omega squared q cosine omega t. So when you take the derivative, it becomes negative sine, and then the second derivative it becomes negative cosine. So we have negative cosine, and then we need to apply the chain rule for 2 times. So we have a omega square here. Okay, so this is d2q dt2. So we have a negative L omega square q, and then cosine omega t. Okay, so actually omega is omega square is 1 over LC. So we will have minus L times 1 over LC q cosine omega t. So this one, L and L can be cancelled. We have a q over c negative cosine omega t. And actually q over c is nothing but v, because q equals zv. So negative v cosine of omega t. Okay, so and here we have v to be 57. So negative 57 cosine of t over square root of LC. L is 12 times 10 to minus third, because 12 millihenry, times 1.5 times 10 to minus 6. Okay. So finally we get negative 57 cosine of 7,500 t, and then V volt, like this. Okay, so and of course this 7,500 is in radian per second. Okay, so this is VL of t. So negative 57 cosine of 7,500 t. Okay, so for the part B, what is the maximum rate di dt max at which the current I changes in the circuit? So actually, we already have I equals negative omega q sine of omega t. If you can't remember, you can still derive it correctly. I equals dq dt, which is d dt q cosine of omega t. So you take the first derivative, it becomes negative q sine of omega t, like this. Okay, so let's try to take the derivative, because we would like to consider the derivative of the I and then take the maximum. So let's take the derivative of it first. So it is nothing but negative omega square q cosine of omega t. Okay, so here we consider di dt max. Di dt max will be nothing but omega square q, which means when cosine of omega t equals -1, then the whole function takes the maximum value. Okay, so in this case, it is nothing but q over LC, which is q over c is v, so which is nothing but v over L. So finally, we have 57 over 1.2 times 10 to minus third power. So which is 4,800 A per S. So this is the maximum rate of change of the current. Okay, so next we consider a more complicated case, which is known as the damped oscillation in an RLC circuit. So here, rather than having L and C, we also have R in series. So whether we put R here or there are actually the same, as much as they are in series. And as I mentioned, it is so-called a lump circuit. So as much as they are in series, even I put this out here, which are actually the same, just a free bit. Okay, so here we do the similar analysis using the power method or the energy method. The energy method. Okay, so the total energy here is UB plus UE, which is this expression, which is actually the same as the previous case. But the difference is that now, however, the total energy decreases as energy is transferred to the thermal energy, because here we have the resistance. So there will be power dissipation or energy dissipation over this resistor. So the rate that the transfer is du dt equals I, negative I square R. So the power consumption of it is I square over R. But here, du dt is actually the total energy of this circuit. So which means that the rate of change of the total energy is a negative value, which is a negative I square R. Negative I square, the energy consumed by this resistor. So when we try to take the derivative of this expression, it should be equal to negative I square over R rather than 0. For 0 case, it is without this resistance. But here, when we have a resistance, then du dt should be this negative value. Okay, so similar as before, when you try to take the derivative, du dt, which is this expression, Li, maybe I can just okay, here. Yeah, like this. So we have Li di dt plus Q over C dQ dt. Here it is equal to negative I square R. Okay, so we can just yeah. Okay, so here it is nothing but this, and then similarly we can just plug in let's say I equals dq dt, and then plug in here. So here it becomes L dq dt, and then times d2q dt2, and then plus Q over C, and then dq dt, and then equals negative dq dt quantity square and then times out. They are a little bit too small. Ouch. Negative dq dt square out, like this. Okay, so similarly, we can also assume that dq dt is not 0, so we can just cancel one of it. It becomes L d2q dt2 and then plus q over c equals negative dq dt times r. Okay, just cancel one of the dq dt. Then we can just rearrange the term and then divide both sides by L. Divide both sides by L. So we have a d2q dt2, which is the first term. So you can see this. Sorry. Okay, so you can see this term is this one. This term is this one. Actually, we need to divide L, divide L, divide L on both sides. So yeah. Okay, so the second term, we move this one to the left side. So we have R over L dq dt with a positive sign, which is this one. And then finally we have this one. 1 over LC times Q. 1 over LC times Q. So like this. Okay, so we get this second order ODE, which is still a homogeneous solution because we don't have a battery here. Okay, but different from the previous case, we not only have the first term and the last term, we also have the middle term, which this term is referring to the losses, of energy. This term. So actually, when we try to solve this second order ODE, then we can get the expression like this. And the oscillation frequency is not 1 over LC anymore, although we still define 1 over square root of LC as omega. But actually, the natural frequency of this circuit is slightly smaller than omega. So we have omega squared minus this term, so which means the total term is slightly less than omega squared, and then take the square root. So this whole term should be less than omega. Oh, let's see why the expression look like this. Okay, so for the potential method, we can, actually this is the energy method, but for the potential method, we can still derive the same thing. So it is Vc, and then this is V out. This is V out. This is VL. So I define VL, positive, negative, positive, negative, positive, negative, back to back, which means that using the KVL, we can quickly see that VL plus VR plus VC to be 0. Yeah, because we define this voltage back to back. Okay, so next, we can try to write, and also we define the current in a clockwise direction. So for VL is nothing but L di dt. And then for the R is still nothing but R times I, according to the Ohm's law. And then VC. And then here we can also write I is C dVc dt, because this is I. So the VC is the potential difference across the capacitor. So I equals C dVc dt, like this. Okay, so here we can try to plug in this one into here, and here. So for the first term, we get LC d2 VC dt2 plus RC dVc dt plus VC equals 0. And then we can just divide LC on both sides. We will get d2 VC dt2 plus R over L dVc dt plus 1 over LC VC equals 0. So actually we get the same equation with two different methods. And here we will try to solve this equation. Let me just. Okay, let me just put it here, and then we can try to solve it. So this is a homogeneous second order constant coefficient ODE. So we can just change the second derivative into S squared, and then R over L, and then first derivative change it to S, and then plus 1 over LC equals 0. Okay, so actually we need to consider the delta, which is B squared minus 4AC, which is R over L quantity squared minus 4 over LC. And we would expect this one to be smaller than 0 for an sinusoidal oscillation, although it is a damped oscillation. Because when delta is larger than 0, it will be exponential function, exponential to negative S1t. S1t, and then exponential to negative S2t. So which is not oscillation, And for delta equals 0, it becomes A plus BT exponential to negative ST, something like that, or positive. You can simply imagine S is a negative value, something like that. So this is not oscillation either. So the only case we concern is when delta is smaller than 0, then it will be damped oscillation. So in this case, suppose delta is smaller than 0, we know that S is a negative R over 2L plus or minus J, and then square root of 1 over LC minus R over 2L squared. Okay, so this is just the high school mathematics for the quadratic equation. So negative b plus or minus square root of b squared minus 4ac all over 2a. So if we simplify as this, yeah, the only thing is that I usually use j to represent square root of negative 1 rather than I. Okay, so this is the real part, this is the imaginary part. This is the real part, this is the imaginary part. Okay, so in this case, we can get no matter I or VC or whatever, even though we just derive VC here, but actually you can actually get d2i dt2 plus r over l di dt plus 1 over lci equals 0, as this is a linear circuit. You can just change VC into other variables. So actually, we can just make it I. So we have I equals exponential to the real part. The real part is negative R over 2L T, and then cosine of omega. Omega is omega prime. This is omega prime. Omega prime to be square root of 1 over LC minus R over 2L quantity square, or omega is 1 over square root of LC, so it becomes omega square minus R over 2L quantity square, and then take the square root. So this is omega prime T plus phi. Actually, when we talk about how to solve second order ODE, I mentioned that it should be exponential to alpha t, and then a cosine omega t plus b sine omega t. But actually, this one is equivalent to this. Actually, we also have. We actually have I0 in the front, as this one can be converted to R cosine omega t plus phi, something like that. So we need a multiplier in the front. So this is the expression, which will be the same as this one. The only difference is that it write it as Q, but here we use I, but yeah, all the things will be the same. Yeah, so we also get exponential to negative RT over 2L, exponential to negative RT over 2L, and then cosine of omega prime t plus phi, and then with this expression, omega square minus R over 2L quantity squared. Here we also have omega square minus R over 2L quantity square, and then take the square root as omega prime. Yeah, so actually we derive how to get this expression. And the point is that if we have the resistance here, the natural frequency or the oscillation frequency is not 1 over square root of LC anymore. It is slightly lower because it is damped by this resistor. Okay, so yeah, to see the comparison between the spring mass system, we can also try to derive it like, as much as we have this spring and then with the mass. Here we also consider the fractional force will be negative B times B, which means that the frictional force is proportional to the velocity, but in the opposite direction, which means that if the object doesn't move, then the frictional force will be 0. But if the object is moving to this side, the frictional force should point to the opposite side. So it should make some sense. So in this case, the force acting on this mass should be negative kx and also negative bv. So F equals negative kx minus bv, and v is the first derivative of the displacement, so dx dt. And then it should be ma is m d2x dt2, so according to Newton's second law of motion. Okay, so we can just rearrange the term. We get m d2x dt2 plus b times dx dt plus kx equals 0. So we can just divide m on both sides. We get the second derivative of x with respect to time plus b over m dx dt plus k over m x equals 0. Okay, so we get a similar second order ODE with constant coefficient. Which means that you can just try to exchange R with B, and then L with M, and then 1 over LC with K over M. Then you'll get the same thing. Let's see, you can try to you can just try to compare these two. So B to be R, M to be L, K over M becomes 1 over LC. Then these two equations are actually the same thing. Same thing. Okay. Okay, so here let's take a look at a sample problem. So here it says a series RLC circuit has inductance L, C, and R to be these values, and begins to oscillate at time equals at time t equals 0. So at what time t will the amplitude of the charge oscillation in the circuit be 50% of its initial value? Note that we do not know the initial value. Okay, but actually we don't really care about it, because when we try to consider what time is half of its initial value, we only care about this term to be 0.5. Then yeah, we assume this the amplitude at that moment is half of the initial value. Okay, so here, as much as the amplitude of charge is Q times exponential to negative RT over 2L, like this. So when it is half of the initial value, then which means that exponential to negative R over 2L, and then T0 is 0.5. We want to find what is T0. So actually we can just take the, so this is nothing but 1 over 2, or 2 to the negative 1 power. So let's take the log on both sides and then take the reciprocal, actually we should take the reciprocal and then take log on both sides. So we'll get R over 2L T0 equals natural log of 2. So in this case, T0 is 2L over R, and then lateral law of 2. Then we can just plug in the value 2 times 12 times 10 to minus third power over 1.5 times lateral law of 2. So this becomes 11 millisecond. 11 millisecond. Okay. And how many oscillations are completed within this time? Within these times. Okay, so here we would like to calculate omega prime equals omega square minus R over 2L quantity square, and then take the square root. So this is nothing but square root of 1 over LC minus 1 over 2L quantity square. And then we can just plug in the values. Then we can know the angular frequency of the oscillation. So this is L is 12 times 10 to minus third power, and then C is 1.6 times 10 to minus 6 power, and then like this, and then minus 1.5 over 2 times 12 times 10 to minus third power, and then quantity square, and then take the square root. Okay. Okay, so this one is nothing but this one is nothing but 7.217 kiloradian per second. Kiloradian per second. Okay, so when we consider the number of oscillation should be the total time. The total time is 11 millisecond. 11 millisecond. So 11 millisecond is 10 to minus third power, and then times 7.217 times 10 to minus times 10 to the third power, 10 to the third power, and then over 2 pi, and then over 2 pi, because omega prime times the period will be 2 pi, or f prime times t will be 1. Okay. Frequency and the period are the reciprocal, and then omega prime times t will be 2 pi. Okay, so this is the number of oscillation. So it is around 12.6 times. 12.6 times. So just in case you don't know what does it mean, I can try to explain this one with this expression. Q equals Q exponential to something cosine of something will be like as much as Q equals capital Q exponential to negative RT over 2L cosine of omega prime t plus phi. It will be something like we have an exponential decaying envelope, and then we have another sine wave oscillating like this. If we don't have this exponential term, then it is a sinusoidal wave as usual. But here we multiply it by, so this is the exponential. This is exponential to negative RT over 2L as the envelope. ENVLOP. Envelope. In Chinese called bao lo. Don't know how to write. Envelope. So it's just like a decaying sinusoidal. So for this question, it's asked about for the initial value is capital Q. It decaying to half of the Q, and then it asks you how many period are there. So it's around 12.6. Okay, so let me stop here today.